Alright, welcome back, guys. We're going to be terminating Chapter 6. So Chapter 6 has been about finding a confidence interval for a point estimate. Okay. Now, in the past two sections, that point estimate has been the mean. Trying to figure out, with a certain level of confidence, where the population mean actually lies, or within what interval. Okay. So we're going to be doing something really along those same lines, guys. This particular section isn't going to be hardly any different from the last two. Okay. We're going to be finding confidence intervals for population proportions. Okay. So in other words, what we'll be doing is trying to figure out within what interval, and we'll have a certain associated level of confidence, does the true proportion of a population lie. And when I say proportion, I mean percentage. Okay, so I'll give you an example. Again, since we've got a presidential election coming up, the proportion could be what percentage of candidates, what percentage of the population favors a particular candidate. Now we rely on polls, right? And all a poll gives us is a point estimate, essentially. Okay, it gives us a statistic, and we use that statistic to generalize about the population. But we don't actually know what the true percentage of the voting population, that's what we'd be talking about here, not the entire population. The population would be all those individuals that are going to vote in the election. What is the true percentage that favor, X candidate? So that's kind of what we're going to be talking about today. All right. So let's look at these learning objectives. Hopefully we can do this one a little less time, since a lot of the theory, conceptual theory, we've really already covered. So we're going to look at how to find a point estimate for a population proportion. We're going to construct these confidence intervals for that population proportion. And then again, keeping in line with the last two sections, we're going to look at figuring out what the minimum sample size required when estimating population proportion. Okay, so again, if we want to ensure that our margin of error stays within a certain bound, what is the minimum sample size that we need to ensure that? Okay, because again, remember that as the sample size gets larger, the larger it gets, the more it approximates the the population. Okay, so, all right. Well, you can think back to when we were talking about binomial distributions and the probability of success in a single trial. We called that, we used P to denote that, okay? So, an example of this is, let's say, we have a coin that's actually weighted, okay? So the probability of heads and tails are not equal. The probability of heads is actually, we'll say, larger. But we don't actually know what that proportion is, okay? So we could perform a binomial experiment in which we flip that coin several times, and we record the number of successes, or the number of heads, and divide that by the total number of flips, and that will give us an estimate for what that actual what the actual weighting of that coin is, okay? Because it's not 50-50. If it's a weighted coin, that means in this example, heads is going to be a more likely outcome. So that would be an example, okay? All right, so how do we find a point estimate? Well, I just talked about it, okay? We take the number of successes, okay? Or in other words, the number from our sample that meets whatever criteria that we're talking about. And we divide that by the total number, the sample size, in other words, okay? So X will represent the number of successes in the sample. And then N, of course, is always going to be the sample size. So X could be, we could take a presidential poll, and X could represent the number of individuals from that poll that favor X candidate, and then we would divide that by the size of the actual poll. Okay, typically those polls I think are around 1,000. And then we would get this point estimator, okay, this point estimate, and we call it P hat. So instead of X bar, like we saw in 6.1 and 6.2, we've got P hat, okay, so it's an estimate based on our sample for what the true population proportion is. And then along that same vein, guys, if P hat is the estimator for the number of successes, then Q hat, 1 minus P hat, would be the point estimator for the number of failures. Or in other words, this could be, in the context of presidential polling, the percentage of the true percentage of the population that favors the other candidate, okay? Candidate Y, for example. All right, well, let's look at an example. It says we've got a survey of 1,755 adults from some country, and 856 said that they were not confident that the food they eat in this particular country is safe. And so we want to find a point estimate for P, the proportion of adults who think the food they eat is safe. All right, now this one's a bit tricky. Well, it's not really tricky, but it's not as straightforward as I guess I would have liked. So the 856, these are actually people that don't feel confident that the food is safe, okay? And so if we're trying to find a point estimate for P, that's the proportion of adults who think the food is safe. So, whoops, hold on just a second, guys. I'm going to pause the video while I get this sorted. Oh, there it goes. Just miraculously came on, my tablet that is. Oh, now it's off. Okay. Alright, well, so to find P hat, we need to figure out the number from this sample that satisfy this condition, that think the food they eat is safe, and divide that by the sample size, okay? Well, the number that actually, this number here, the 856, these are the ones that are not confident that the food is safe. So to find the number that do think that the food is safe, we need to subtract 856 from the sample size. And we get 889, okay? So to find P hat, our point estimator, for the true population, or the true percentage, or proportion, same thing really, that feel that the food is safe, we're going to divide the number from our sample that think that the food is safe by our sample size. And this is always going to be a decimal, guys. Okay. Let's see. Well, I've already got the 889 in there, so I'm just going to divide it by the sample size. And I'm going to get, let's carry this to 3 decimal places, 0.512. Okay, so in other words, this would be our estimate. You could say that, based on this sample, 51.2% of people from this country think that the food is safe. Now we know this is not the true percentage, but we could use this to figure out a confidence interval. We could build a confidence interval, okay, once we calculated the margin of error for where the actual proportion or percentage of the population thinks the food in this country is safe actually lies. I know that was kind of a long sentence, but all right, so so we know how to find a point estimate, okay, or point estimator. Just a number from the sample that satisfies a certain condition divided by the sample size. So guys, it's the same thing as finding the mean, really. Well, you know, for the most part. All right, so how do we construct a confidence interval? Well, pretty much the way we've been doing, okay? We calculate the margin of error. And again, you know, if you're just looking right here, the margin of error is going to be affected by the sample size, okay? So as the sample size gets bigger, because n is in the denominator here, the actual margin of error will get smaller. And then you can see we're going to be using p hat and q hat, okay? So we're going to be using the actual statistics from the sample. We're taking the square root again. This right here, this p hat and q hat, this is the same thing as the standard deviation, okay? And then we're going to be multiplying that by the associated critical z-score. Okay, so first thing we want to do is we need to find our point estimate, okay? So we'll do that. And then I didn't really talk about this, but it says verify that the sampling distribution of p hat, similar to the sampling distribution of all those theoretical sample means, like if you were to take a bunch of samples, how is that actual sampling mean distributed? Well, it's normal, okay? And so it's going to be normal for p hat as well, as long as it satisfies either of these conditions, either one. N times p hat is greater than or equal to 5. So this is, in most cases, going to be an easy condition to satisfy, okay? Now, to the extent that we're not really going to worry about it in this section, we're going to assume that p hat is normally distributed, okay? Then we're going to find that critical value, or that critical z-score that's associated with that specific level of confidence. So we've been doing this. Now we're going to calculate the margin of error once we know that, okay, those parameters. And then, like always, whatever that margin of error is, we're going to both subtract it and add it to our point estimate to get the lower and the upper bound of our confidence interval, okay? All right, so let's plunge right on in here to example 2. So it says, use the given confidence interval to find the margin of error and the sample proportion. Well, here what they've given us, guys, is the actual confidence interval. So p hat, or the sample proportion, is always in the center, okay, just like x bar is always in the center. So what we could do, like always, is we can take both the upper and lower bound and average them, okay, and that average will be the center point, or the midpoint, in other words. Oops. Okay. Yeah, so what we're doing is we're finding the midpoint, okay, because the midpoint will be the population proportion. All right. So I'll do this real quick. I'll use my mouse. It's a little quicker. Oops. Divide this by 2, and we get 0.782. Okay, so p hat is evidently 78.2%, in other words. Okay, and then again, what has happened to construct this confidence interval is this point estimate has had the margin of error both added and subtracted from it. Okay, so to figure out what that margin of error is, I could take the upper bound from that interval, and I could subtract from it p hat. That'll tell me what that margin of error is. And guys, I believe that this is going to be 0.013. Okay, now these margin of errors are going to be small, okay, because p is just a decimal to begin with, so the margin of error is going to be an even smaller decimal. So anyway, it's about 1.3%. Alright, so now let's kind of get to the crux here. So we're actually going to find some confidence intervals, okay? Now, to be consistent with the previous two sections, we'll do one manually, and then I'll show you how you can use your calculator again, okay? So here we've got a survey of 2,579 adults, and 1,358 say that they made a New Year's resolution. And we want to construct two different confidence intervals, okay, for the population proportion. So what we're assuming here is that we're trying to find the population proportion of individuals that made New Year's resolutions, okay? All right, so to do that, the first thing we want to do is find p hat. Okay, well, that's going to be the number from our sample that made resolutions divided by the size of our sample. All right, so, yeah. Alright, so I'm going to carry this actually to 4 decimal places, and part of the reason is because I still need to find the margin of error, and so this is going to be a value that I'm using in some future calculations, so I want it to be fairly accurate. So to 4 decimal places, this would be 52.66%. All right, okay, so that's my point estimator, and it's around this that we'll construct our confidence interval. We'll do the 90% first. We'll do this one by hand, okay, and then we'll do the other one using the calculator. All right, so the margin of error, if you were to scroll back up, it is equal to our associated critical z-score divided by the square root of p hat times q hat divided by the sample size, okay? So the next thing I could do is I could go ahead and find q hat. Well, yeah, I'll just do it this way. I'll just subtract. The other way to do it, guys, would be to subtract this number from the sample size and divide that by the sample size. That'd be another way to get q hat. But since I already know what p hat is, I can just subtract it from 1. So I'll just say 1 minus that value that I've already done in my calculator. I'll do second and then answer right here. And carry this to 4 decimal places, so 0.4734. Okay. All right, because we need to know these. And then we know the sample size. We need to find that z-score. Okay. So the z-score associated with a 90% confidence interval. Guys, remember, what you'd be doing here is if you're trying to find the z-score such that you have, well, 2 z-scores, I guess, technically, such as you have 90% in the middle, it means you have 10% in the tails together or just 5% in the tails individually. So you could use your calculator to find that z-score such that 5% of the area is to the left. Now it'd be negative, remember, but you just take the absolute value of that. But what I'm actually going to do is pull up the previous notes from 6.1, because this is more convenient, and just look at my table here, okay? So guys, utilize this if you need to. So the associated z-score for a 90% confidence interval is 1.645. So that's what I'm going to go with. 1.645. And now I'm going to plug all these values into my formula times the square root of p hat is 0.5266 times q hat, which is 0.4734, and then this is divided by the size of the sample, which is 2,579. Okay, so let's plug all this in. Well, I've got, what I could do is just, since I've already got q hat in there, I can go ahead and multiply it by p hat, 0.5266, hit enter. Then I can divide that by the size of the sample, hit enter. Look, this e here to the -5, this means, this is a pretty small decimal. And then I can take the square root of this answer. So I hit second answer. See, this saves me from having to type in everything individually. And I get this value, and then I'll multiply this by that critical z-score, critical z-value. And we're going to get a margin of error of, and again, remember, these are going to be kind of small. This is roughly 1.6%, okay? I'm going to call it 0.0162. Okay, oops. All right, so then to find my lower bound, I need to take p hat and subtract from it the margin of error. And then to find my upper bound, I'll take p hat and add to it the margin of error. Okay, so I'm going to do this in the calculator. All right, so p hat is 0.5266. I'm going to say minus that previous answer, because that's the margin of error. And I'll round this to 3 decimal places. So this will be 0.510. So the lower bound is 0.510. And then my upper bound, just do it very similarly. The point estimate, the p hat, now plus that margin of error. And we get 0.543, 0.543, okay? So this margin of error for a 90% confidence interval goes from about 51% to 54.3%, okay? Now what I'm going to do is show you how you can do this using the calculator, and this is really convenient, guys. So you come over here to stat again, just like we've been doing. You go to tests, and instead of doing a z or t interval like we did in 6.1 and 6.2 respectively, you're going to come down here and go to A, where it says 1 proportion z interval. And you click enter, and you'll just put in these values. You can see I've actually already done this. X was 1,358. Plug in the value of n, your confidence level, and then come down here to calculate. Whoops, I skipped it. I just hit enter too many times. So let's verify here. There we go. And look what we've got, guys. This to 3 decimal places would be 0.510, and this to 3 decimal places would be 0.543. Okay. So I'm going to use this from here on out, okay? Because we know how to do it by hand now. We know essentially what we're doing is we're taking p hat and we're both adding and subtracting the margin of error from it. All right, so what about the confidence interval when C is 95%? Well, we've already, let me go back here to stat, go to calculate again, or not calculate the tests, and one proportion Z interval. I've already got X and N in there, and I'm just going to change my confidence level to 95. Now, well, here it is. Let's go ahead and write it down, okay, and compare it with the 90% confidence interval. So this one rounded to 3 decimal places. The lower bound would be 0.507, and then the upper bound would be, if I round this to 3, it would be 0.546. Okay. All right, so now to compare the two, so the interval right here associated with this higher level of confidence is a little bit wider, if you notice, okay? And that's because, you know, if we want to have more certainty, then we're going to end up with a wider interval to make sure we capture that population proportion, the true population proportion, okay? And then with a lower level of certainty, we end up with a narrower confidence interval. It might even seem a bit anti-intuitive depending on how you look at it, but anyway, guys, that's how you find a confidence interval for a population proportion, okay? Let's do another one. And then we'll look at figuring out that minimum sample size to ensure that our confidence interval doesn't exceed the bounds that we want, or the margin of error doesn't exceed a certain threshold. All right, so we got this figure down here. It's from a survey of 800 U.S. adults, and it says construct a 99% confidence interval for the population proportion of U.S. adults who prefer to get their news from television. So evidently, this gives us the percentage of U.S. adults who prefer to get their news from each platform. So you got digital platforms, television, radio, and print publications. And because we're using a newer edition of this book, guys, it's probably maybe fairly accurate, okay, 52% from digital platforms, okay, so online stuff, in other words. But we're looking at television, okay, so there's 35% from this sample that prefer to get their news from television. So evidently the number of these 800 U.S. adults that were sampled, 35% of them said television. So we already know the point estimate, okay? P hat is 0.35, okay? So I'm going to use the calculator to find the confidence interval. Now, you'll notice when I come in here, it asks for X. There's not a place for P hat. And the reason is because the calculator typically just calculates P hat. So here we've got to figure out what X was. Well, X was whatever 35% of 800 is. So guys, you can literally type that in. 0.35 times the size of the sample, which is 800, and that would tell you what X had to have been. The number of adults in this survey that actually said television. And then, of course, we want to change. See, it actually went ahead and calculated it when I just scrolled or came down here. And then the size of the sample, N, is 800, and then we want a 99% confidence interval. Okay? Calculate this, and we get our lower bound. I'll carry this to, I guess, 3 decimal places. 0.307 if I round. And then the upper bound would be 0.393 if I round. Okay. So the true proportion based on this sample, the true proportion from the population of U.S. adults who prefer to get their news from television would be we can be 99% confident that it would be somewhere within this range. So this is actually a fairly large interval here, 30.7% to 39.3%. And the reason it's so large, guys, is because that's a very high level of confidence, 99%. Okay, that's close to 100. All right, and then graph, I've got a little graphic down here that shows this is p hat, and this is our confidence interval. Okay, so we're saying that, essentially what we're saying is that if we took 100 samples, or 100 surveys of the same size, that 99% of those means, or not means, but proportions would fall in here, okay? All right. Okay, well, let's look at this last piece of this, okay? So, just like we did in 6.1, if we know the margin of error and the sample size, then we can manipulate that margin of error formula. Okay, I'll come back up here. We can manipulate this and we can solve it for n. And if you were to do that, I'm not going to do it for us, it would give us this formula. Okay, and so if we know what we want our level of, or our margin of error to be, or to be within, no larger than a specific value, we can plug that in here along with the sample statistics and our associated z-score, and we can find what the minimum size of the sample that we need to have is, such that the margin of error is no larger than this value. Okay. And then again it says if n is a whole number, we always want to round up. Now, note this last bullet point here. It says, note that this formula assumes that you have preliminary estimates for p hat and q hat. But if you don't, you're going to use these as your estimators, okay? 50% and 50%. All right, well, let's look at example 5 here. Most of the time, you're going to know, but I think this is fascinating because this is saying, okay, well, I don't even have to take a sample then, and I can use these estimators, okay, to find, I can specify a specific margin of error, and I don't even have to take a sample, and I can use these values and come up with a minimum sample size, okay? And this makes sense too, because before you do this, you're trying to, you don't have anything to go off of. So you're trying to figure out, well, what's the minimum size that I need my sample to be such that I can ensure the margin of error is no more than 1% or 4%, whatever the case may be. All right, well, let's look at example 5. So a researcher wishes to estimate with 90% confidence the population proportion of adults who think Congress is doing a good or excellent job. Our estimate must be accurate within 3% of the true proportion. Okay, so this is the margin of error that we want to use. Okay, so I'm going to go ahead and write this down. Now, you got to make sure you convert that to a decimal though. This is very crucial, guys. All right, so part A, it says no preliminary estimate is available. So because of that, we're going to use these estimates right here. Find the minimum sample size needed. Okay, so for the first part, we're using 50% as our point estimates. And guys, I don't know if you listen to the news, this estimate is actually given. I hear this a lot because I listen to NPR, whenever I'm driving, and they'll talk about, a percentage of the U.S. populace that thinks that Congress is doing a good or excellent job, and not surprisingly, it's a very low percentage. Okay, because most people, myself included, feel like Congress doesn't do all that great of a job. Okay, but anyway, those numbers that they give, those are estimates. Okay, so those are like our values for p hat. All right, well, let's go ahead and do this. We're going to use this formula. Okay, so our minimum sample size is going to be our 2-point estimates, and this will be our z-score. If you remember when I glanced at that table earlier, the z-score associated with a 90% confidence interval is 1.645. And we'll divide this by our margin of error, which is 0.03. In other words, 3%. And guys, you've got to square all of this. Okay. So I'm going to plug this in my calculator. I'm ready to compare these results because this is interesting. Alright, so 1.645, and divide that by the margin of error. And enter, and I'm going to go ahead and square it. And then I'm going to multiply it by each of these two values. 0.5, whoops, I need to go ahead and say times though. So times, wait a minute. So, there we go. I needed to make sure it referenced my previous answer. Okay, so times. Now you could type in here 0.5 times 0.5, or you could just say times 0.5 squared. And anyway, we get this, okay? So if I round this to the nearest whole number, this would be 752. So when we don't actually know a point estimate, when we haven't actually taken the sample, but we want to have a margin of error no greater than 3%, then we need our sample size to be at least 752. Okay. All right, so now let's look at part B. It says find the minimum sample size needed using a prior study that found that 26% of the respondents said that they think Congress is doing a good or excellent job. All right, so now we have an actual point estimate from a previous sample, or from a previous study, okay? So again, we're still using the same formula. Whoops. I need to write not E equals, but N is equal to 0.26, okay? So if, in this case, P hat from that previous study is 0.26 or 26%. So Q hat would be, if you subtract, it would be 74%. Okay, and then again, this stuff's going to stay the same. Now your critical z-score, and then your maximum margin of error. Again, we'll just type this into the calculator. Alright, so 1.645, divide this by that maximum margin of error that we want. We're going to square that. Then we're going to multiply that by those 2 point estimates. 1 times Q hat. I'm getting a decimal here. So you made a mistake somewhere, because I should not be getting a decimal. I should be, getting a decimal, but it should definitely be, because we're talking about a sample size here. Let me try this again. so 1.645 divided by the margin of error. And I'm going to square this. Well, that is the same as we got earlier. Okay, so we'll multiply this by 0.26. Okay, yeah, we're going to multiply this by 0.74. I think I must have mistyped one of those decimals. But anyway, this makes more sense. Okay, so if I round up, it's technically not to the nearest whole number. You always round up. So 579. Okay, this is our minimum sample size that you need to ensure a margin of error no greater than 3%. And then part C says compare the results. Well, this is interesting because this minimum sample size is smaller than this. And the reason, guys, is because we actually have a point estimate from the previous study. So we have a lot more information, so we don't need that sample to be as large. Okay? Remember, statistics, guys, is all about how much information do we have available. Okay? It's all about certainty. How certain can we be? So here we have more certainty because we've got a point estimate from a previous study. Right here we were just kind of in the blind, so that necessitates a larger sample size. So anyway, well, that pretty much concludes this section, guys. So the next video will be delving into hypothesis testing, and that's something that you're going to need for your statistics project. Okay, we'll cover 2 sections in Chapter 7, and so we're nearing the end of the course. We've got 2 sections in Chapter 7, and then we'll have 2 sections, I believe, in Chapter 9. So really just 4 more sections. All right, so I'll see you in the next one, guys.